Okay. So what does it mean to be invariant? So okay, so G has a property P, and G prime is isomorphic to G, then G prime has property P. So that's the definition of it. Okay. Now the concept of invariance has to do with, well, how do you prove that something's not isomorphic? A lot of times it's easier to prove that something is not isomorphic by showing that it does not contain the same property of G. All right, so if you want to show that G and G prime are not isomorphic, well, then show that they lack an invariant property, okay? So what is meant by an invariant property that will prove that something's not isomorphic? There's actually 10 of them. Okay? So 1. Has n vertices, okay? So if you have two graphs and you want to show that they are not isomorphic, what is one of the easiest ways to show the two graphs are not isomorphic? They have different numbers of vertices. Okay, so you have two graphs that have different numbers of vertices that are not isomorphic. Okay? As m edges. Okay? If they have a different number of edges, they're not isomorphic. Okay? So you have different number of vertices, different number of edges. Those are not isomorphic graphs. Okay? That's a really easy way to prove that something is not isomorphic. Okay. And there's actually 10 of these, so I'm just going to start writing them down. So, as a vertex of degree k, okay, has m vertices of degree k, okay, so if you have one graph that has a vertex of degree, I don't know, 7, and the other graph doesn't have a vertex of degree 7, they're not isomorphic, okay? If you have one graph that has 3 vertices of degree 7, and the other graph doesn't have 3, they are not isomorphic. Okay, so there's a lot of restrictions on these. And so vertices with certain degrees, okay, has a circuit of length k. So if one of your graphs has a certain circuit and the other one does not, they are not isomorphic. Okay. has a simple circuit. Link K. 7 has M simple circuits. Of link K. We just got 3 more and then we'll do some examples. Okay, so M simple circuits of length K. You'd say 8 is connected. 9 has an Euler circuit. And 10 Hamiltonian circuit. Okay, so if one graph has any of these properties and the other graph does not, then it is not isomorphic. Okay, so if you lose any one of these, going from one graph to the other, they're not isomorphic. So let's look at an example of this. Actually, I guess I have room on this page. Okay. Now the question becomes, are these graphs isomorphic? Yes.
I don't think so because there's not
There's not what?
not many edges because you have
Yeah.
2 edges on just G and O that do like full loop 2 vertices, and then on just G prime you don't have that.
Okay, well, let's ask ourselves the question of the edges. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. They have the same number of edges.
They have a different number of vertices.
They have a different number of vertices. So if you just look at this, this is 1, 2, 3, 4, 5. This has 5 vertices. Okay. And then this one has 1, 2, 3, 4, 5, 6 vertices. Okay. So we would say that this is not isomorphic. Okay. So having a different number of vertices or a different number of edges that's an easy, really easy way to prove that something is not isomorphic. Okay. Just counting the vertices or counting the edges is probably the easiest way to just prove something that's not isomorphic. What gets more confusing is that what happens when you have the same number of vertices and the same number of edges. Okay. So just having a different number of vertices or a different number of edges that's the flat out easiest way to prove that something is not isomorphic. But what if we had something that had the exact same number of vertices and edges? Okay, so let's say okay. Now on this graph right here, if I count the number of vertices, I get 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So they have the same number of vertices. Okay. If I count the edges, I get 1, 2, 3, 4, 5, 6, 7, 8. And if I count vertices, 1, 2, 3, 4, 5, 6, 7, and 8. The two in the middle, the last two. So they have the same number of vertices and the same number of edges. And now something like this, if I wanted to say, how would I justify that these two shapes are not isomorphic? Well, we have our list of possibilities of invariance, okay? So if one property is true for G, then the other property would have to be true for G prime for them to be considered isomorphic, okay? This is where you start getting into circuits, okay? So one of our statements says that an invariant property is that if G had a circuit of length K, okay? Let's remind ourselves of what a circuit is that, it's a closed walk and it doesn't have any repeated edges. Okay. So, if we look at this, if we consider a closed walk on this first one, what would be a circuit that would exist upon this one? Well, I could go from this vertex to this one, to this one, to this one, right? Okay. So this one has a circuit as a circuit of length 3. Okay, because I can do a closed walk from this point, this vertex right here, just go down, over, and back up. And so I can create a circuit from that. Okay? Now, can you find a circuit of length 3 on G prime? Well, no. It seems like every circuit that exists on G prime, to get back to where I started, I have to go down here, over here, 3. All of them would have to have at least length 4 to get back to where you were, length 4 or greater to get back to where you started, okay? So this guy G prime right here does not have a circuit of length 3. G prime does not. And so we would say let's phrase it this way, not isomorphic. Okay. And so I was referring to isomers a minute ago, and let's actually have, before I get into the concept of trees, now in chemistry, they use a lot of trees to represent different chemical compounds, but let's look at the isomers . Isomers are non-isomorphic ways that C5H12 can actually exist. So 5 carbon atoms and 12 hydrogen atoms. When we talk about discrete math, actually chemistry comes a lot into my mind. All right, well, let's do this in the easiest standpoint. There's going to be 3 of them. And so if I look at the isomers associated with C5H12, okay, well, let's do the easiest one first. And so we would have hydrogen bonded with carbon, with hydrogen, carbon, hydrogen, carbon, hydrogen, hydrogen, carbon, hydrogen 1, 2, 3, 4, and that's hydrogen, and then that's bonded with a carbon, which is bonded with a hydrogen, which is bonded with a hydrogen, which has to be bonded with a hydrogen. And so let me count all my guys out. And so I got 1, 2, 3, 4, 5 carbons, and 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12 hydrogens. And remember that hydrogen is only gonna share one bond, while carbon will share four. Okay. Now, this is one of the isomers of C5H12. And so when somebody says just the compound C5H12, there are other ways for it to actually form, okay? So what would be another isomer of C5H12? If I went, okay, I gotta make sure I have 5 carbons and 12 hydrogens. And so if I went nitrogen bonded with carbon, bonded with hydrogen, which is bonded with hydrogen, which is bonded with carbon, which is bonded with carbon, which is bonded with hydrogen, which is bonded with hydrogen. Sorry, I lost this one. Okay. Which is bonded with carbon, so that's 1, 2, 3. Which is bonded with carbon. 1, 2, 3, 4, 5. Which is bonded with hydrogen, which is bonded with hydrogen, which is bonded with hydrogen, which is bonded with hydrogen. Hydrogen, there's a hydrogen, there's a hydrogen. And so that's 1, all right, 1, 2, 3, 4, 5. And I got my 5 carbons in there. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and I got my 12 hydrogen bonds in there as well. Okay. Now, when talking about just between these two, why would these two be non-isomorphic? Okay, we have 5 carbons and 5 hydrogens. Hence, we have the same number of vertices. Okay, and if I count the edges, 1, 2, 3, 4, 5, there's going to be the same number. Let me count. 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16. 16 edges on this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. They have the same number of vertices and the same number of edges. Okay? And now, these two things are actually known as what is a tree. So they contain no circuits. There are no closed walks.
Is it because the degree of that CH bond?
But no, the degree of the carbon at the bottom would still be 4. Because it has the 4 bonds. It's bonded with this hydrogen, and that carbon. Okay. So all of the carbons still contain 4 bonds, meaning the degree of the carbons is still, the degree of the vertices, which we're considering the carbons, is still 4, okay? And the degree of the hydrogen atoms is always going to be 1, because that's, when you're talking about chemistry, that's the way the electrons bond together within their fields. So there is this type of one-to-one correspondence between the carbon atoms and the hydrogen atoms. The question becomes, there was a second part of that statement when I was talking about isomorphisms, that the edge to endpoint function has to be preserved. Okay? Now, in this problem right here, all of the edges to endpoint are going carbon, carbon, carbon like that. But in this problem right here, your edge to endpoint is different, because if you consider a single endpoint on this one, the edges on either side would correspond to a carbon, and the edges on either component would correspond to a hydrogen. But for this guy right here, what's happening, it's actually got 3 edges corresponding to carbon atoms, and only 1 corresponding to a hydrogen atom. So the edge to endpoint function is not preserved, because you have another carbon on there. So you actually have a single vertex with 3 edges going to carbons, whereas you only have 1 edge that is going to a hydrogen. And so the edge to endpoint function is not preserved in that sense. And there's actually another isomer that we can talk about with carbon, with C5H12. And so the third isomer of C5H12 is that you would have a carbon connecting to a carbon, connecting to a carbon atom, connecting to another carbon atom, connecting to another carbon atom, okay? And then this would connect to a hydrogen, this would connect to a hydrogen, this would connect to a hydrogen, 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 and hydrogen. Okay? So for your third isomer, I mean, how is the edge to endpoint function not preserved? Is that on your first C5H12, every carbon was connected to 2 other carbons. Okay? And then on this one, on the second one, we had, well, there's 1 carbon connected to 3 carbons. Okay? And then on this last one, this last isomer, we actually have 1 carbon molecule that is connected to 4 other carbon atoms that all each have their hydrogens going on. Let's make sure we have all of our hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so these are non-isomorphic, but they still have the exact same number of carbon and hydrogen atoms.